Hey everyone, welcome back. Today I wanted to take a look at Z80 assembler directives. And so, as you may be familiar with already, assembler directives are something we use when creating a Z80 assembly language program using an assembler. And it may initially be confusing to understand the difference between assembler directives and Z80 assembly language instructions. So we're going to take a look at that as well. And if you take a look here, I've got a program up on my screen here that it's quite a long program, and just to give you a bit of a spoiler alert, we're going to be taking a look at this program in detail, I think in the next video probably. But as you can probably tell, this program contains many examples of assembler directives. So before we take a look at that, let me just explain that the difference between an assembler directive and a Z80 assembly language instruction is obviously a Z80 assembly language program requires instructions for the computer to operate once that program gets assembled into machine code. Assembler directives, on the other hand, they are instructions specifically for the assembler to carry out, and they don't get converted into machine code instructions that the computer will later carry out when it executes the program. And today we're going to look at, I think, 4 directives in particular. One we've already looked at, which is the org instruction. Another one which we've also already looked at in previous videos, which is labels, and we're going to take a look at them again today. And then a few other ones we'll look at, which is the EQU instruction, as well as the define byte and define word instructions. So let's go ahead and start taking a look at those right now. So if we take a look at the top of our program here, we have an org instruction, which is an assembler directive, which we already know tells the assembler where in memory to store our machine code program once this assembly language program gets converted into machine code when it gets assembled, which will get stored in memory beginning at location 30,000 in this case. So that is what the org assembler directive does. It tells the assembler where to store our machine code program once it gets assembled. Now let's take a look at the next instruction here, which is main, and you can see it's colored in pink. And all these pink words that you see on the screen here are actually labels, which we've taken a look at before. And labels are an assembler directive, which are incredibly useful for us. They're very powerful features of the assembler, and they are probably the most useful feature of the assembler that makes our programming life a lot easier as compared to creating a machine language program from scratch using pure machine code. So how do labels work? Well, a label in an assembler takes the place of something else. It can take the place of an address, or it can have a value of an actual number. So for example, if we take a look here at this main instruction, since it just says main all by itself, and it's a label sitting on a line all by itself, in this case this label is taking the place of an address. So as we know, the machine code bytes get stored in memory addresses. When this assembly language program gets converted into machine code, every instruction and every bit of code in the resulting machine code program will have to live in memory somewhere at certain addresses. And this main instruction is a pointer to an address in memory where some part of this code will live. So which part of the code will actually live at this main address? Well, if we take a look here and we try to figure out where the next actual byte of code in our program will be, that will be where this main address is pointing to. So here we have our main instruction, and then here we have just a comment. So comments don't take up any memory when the program gets converted into machine code, because the comments don't get converted into machine code. So we can ignore this comment. And the second line is a comment as well. And the next line here is a call instruction. So a call instruction is an actual Z80 assembly language instruction that will get converted into machine code. So in this case, you can see our main label up here will be pointing to the address where the code for this call instruction will be stored in memory. So that's the purpose of our main label up here. It will simply act as a pointer to the location in memory where the code for this call instruction will be living, because the call instruction is the first piece of actual code after our main label up here. And if we take a look down here at these other labels, here's a label called Edge Health, here's a label called Edge Gold, here's a label called Edge Strength, here's a label called Print Vals. Now these labels, they also contain values, but what values do they contain? We'll take a look for this Edge Gold label, for example, and see if we can find it. So right down here, you can see we have another Edge Gold label, And this AdGold label is again taking the place of a memory address, so it will contain a value that points to a memory location. And which memory location will it point to? Well, again, we just take a look for the first piece of actual code that exists after this AdGold label. And here on the line below it, we have another comment, which is not part of the code. And here we have an LD instruction, which is an actual assembly language instruction. So that will be converted to code. So in this case, this AdGold label here will contain a value which equals the memory location that stores the code for this LD instruction. Now let's take a look at another use for labels. And if we take a look at, let's say, this label here, which is called print_str. Let's see how we've used this label in our program. So here you can see this print string or print_str label exists on a line of code that calls a subroutine. So this assembly language instruction is a call instruction. A call instruction, if you don't already know, is similar to a go_sub instruction in BASIC, which calls a particular subroutine and then expects the program to return back from that subroutine. Well, it's the same thing in assembly language. A call calls another subroutine which exists in the machine code program, and then that machine code subroutine will return control of the computer back to the place that called it. So here we have an instruction that will call a subroutine, but a subroutine obviously exists at a certain location in memory. So let's take a look at this print_str label in our program and see how it's being used. So let's just scroll down to the bottom here, and you can see if we take a look at this line here, and again we'll be looking at this program in detail I think in our next video, so don't worry about what this program is actually doing right now. We don't need to concern ourselves with all the instructions in this program for now. But one thing I want to point out is this line here, line 76 in our assembler, and obviously assembly language programs don't use line numbers, they're not basic programs, but this is just a tool in our assembler to help us keep track of the different lines in our assembly language program. So here you can see there's a return instruction, and in this case the return instruction is the last line of our actual program code. But then you can see we have a bunch of other code down here after this return instruction. Well, this code after our last return instruction from our actual program contains code that is not actually executed as part of the program when it's being executed. And we're going to take a look at these instructions in a moment. But first I want to go ahead and continue to look for that print_str label that we discussed a moment ago. And if you take a look right here, here it is right here, print_str. So how are we using this print_str label in this program? If we look at this print_str label, it's followed by the word or the instruction EQU. And EQU stands for equals or equates to, and here we have a value after it, 8252. So in this case, the EQU instruction is assigning a specific value to this label. So this print_str label is going to contain the value 8252. A hard-coded specific numeric value that's going to be contained within this print_str label, kind of like a variable. So in this way you can think of this label as a variable because it's going to be containing this actual numeric value. So here this print_str label is containing a value, but it's not a value that points to a memory address. In this case, it's a hard-coded specific numeric value. And if we see how this label is being used in our program, it's being used right here in line 64. It says call print_str. So this is an instruction that's going to call a subroutine located at whatever value is contained within this print_str label. And this print_str label, as we just took a look at, contains the value 8252. And if you take a look at the comment I've entered here, it says ROM routine to print string. And then it's got some other instructions after it, which are not important for us to look at right now. But the interesting thing that we need to know about what this line is doing is it's assigning 8252 to this print_str label because it's going to use that label to call a subroutine which exists in the computer ROM. And if you're not familiar with ROM subroutines, you can maybe watch the video that I made about 8-bit computer architecture, where it describes how ROM is a type of memory which contains code that the computer needs to start up and execute and perform certain tasks. And the ROM memory also contains subroutines that the computer uses to perform certain functions. And we can actually access some of those ROM routines to perform useful functions for ourselves. And in this case, this program wants to access a subroutine located in ROM memory, and specifically that subroutine is located at the memory address 8252. So that's a memory address in ROM memory. And we can see here at address 8252, there must be a subroutine that we're interested in accessing. And we're going to do that by calling it, but we're not going to call it using this number 8252. We're going to call it using this label. And we do that up here when we call it right here in line 64 with this instruction call print str. Now we could, if we wanted to, replace this label with the actual number, with 8252, and that would work as well. However, you can see how useful it is to use labels because we no longer have to remember what that number is. All we have to do is declare that number or assign that value to a label down here, and then we can simply use that label whenever we want to call that subroutine. And that's what we're doing up here. We're calling the print str subroutine right here in line 64, and it's going to call the subroutine located at the numeric address that's contained within our print str label. So I know I took a long time to explain that, and it's really not complicated. It's just assigning a value to a label. So the way labels work generally is they can be used to assign values that point to a specific memory address, or they can be assigned manually by hard coding a specific numeric address into them using the EQU instruction, which we've done here. So now we know that the EQU instruction assigns a particular value to a label. Now let's take a look at another use of the EQU instruction. And so if we look at the line above it here, which has a label that's called strength, S-T-R-E-N-D, which stands for strength string end, and we're going to explain how this line is used in the next video. But if we take a look at exactly what this line is doing, you can see it has a label called strength str end, followed by this EQU instruction, and then it contains just a single $sign. So a $sign in this assembler represents a hexadecimal value. In this case, there's no value assigned after it. And in fact, this instruction line in our program doesn't contain any actual code because these EQU instructions don't get converted to machine code, so they don't get converted into bytes of data. Therefore, they don't take any space in memory once the program gets assembled into machine code. And here, what is this EQU instruction doing that contains no number after it? All it has is a single $sign after it. So without getting into exactly the details of how this part of the program works, basically what we're doing here is we're using this label to point to a memory address, but in this case it's pointing to a memory address that contains nothing. So just as we assigned labels before to represent memory addresses, like up here if we look at this print CR label, that represents a memory address where the next instruction code will be located. But down here, this strength str end label will be pointing to, again, a memory address that is whatever memory address is the next address. And in this case, I'm using this label as a marker to indicate a particular position in memory. And again, you'll need to watch the next video to find out exactly why I'm doing this. But this is how we can use this particular label to represent a memory address location. However, this can create some confusion, and we'll discuss why that can be confusing in a moment when we take a look at our next instruction, which is the DEFB instruction, which stands for define byte. So define byte is a way that we can store data in memory in an assembly language program. Now these bytes will get converted into machine code when the program gets assembled, but in particular why we're using this define byte instruction is because we want the assembler to know that these bytes of data that we're going to be storing after this define byte instruction are not assembly language instructions that we want to get converted into machine code. So here you can see on line 79 here, for example, we have a label called CR code. We have define byte followed by a single number 13. So how this line is going to work is it's going to assign a memory location address to this CR code label, and that memory address will contain the value of 13 in decimal. And we can use this method to store both numeric and string values, as we can see in our next line of code right here, which starts with another label called health str, which stands for health string in my program. So this line has a label called health str, followed again by the define byte instruction, but this time the define byte instruction is followed by a string of data contained within quotes. And you can see here it contains a string called health. So obviously I'm going to be using this health string to print the value of the health attribute for a character in my game. And in this case, instead of defining a number to be stored in memory, we're defining a whole string of characters. So let's take a look at exactly how that works. So first, let's go ahead and assemble this program. And I'll do that by going File, Assemble. And it's asking me where to store it, but I'm not going to indicate where to store it because I have an org instruction at the beginning of my program, which we all know by now will already indicate where this program should be stored in memory once it gets converted to machine code. But there is one other thing I want to take note of here, which is on this window that pops up, there's an option here that says Transfer Labels to Debugger. So that sounds like an interesting and important feature, which it is, and I'm going to show you why right now. So let's turn on this Transfer Labels to Debugger option right here because we have a check mark, so it's enabled. And what that's going to do is transfer all of these labels that we just took a look at into our debugger. And we'll take a look at those in a moment. So I'll go ahead and assemble the program now. So now that our program is assembled, let's go ahead and open the debugger. And we'll go back to discussing what I was mentioning before, which is how we are storing values in memory using the define byte instruction. So let's go ahead and take a look at these labels. And we can do that by just opening this tab here that's called Labels/Comments. So I'll click on that. And you can see here it brings up a list of the labels that are used in our program. And if we take a look right here, there's a label called Health STR, which is our label that we used over here, where we used it to store a string of data in our program. And the string of data has this word health in it. And let's take a look over here what value this Health STR label actually contains. So as we discussed before, labels can contain memory addresses. And in this case, if we take a look here, this Health STR label contains a value of 30124, which will be the memory address that contains these bytes of code that we're saving here in memory. And while we're here, if we take a look at another label, let's say we look at this print CR label, which we know also contains a memory address where the next chunk of code will begin. So in this case, this print CR label, for example, will be pointing to a memory address that contains the next byte of code in our program, which will be this byte of code here, which is DEFB 13. So DEFB is not an instruction that will be converted into machine code. It's an assembler directive, but this directive tells the computer to store a byte of data in memory. So our next byte of data in the program after this print CR label should be this byte of data right here, 13. So we should expect that print CR, and if we look over here, we can find our label print CR right here, contains a value of 30117. And we would expect that memory address to contain a value of 13 in decimal. So let's go take a look at that. So 30117 is the address we're interested in. So let's go to our disassembly tab here. And we'll search for 30117 by entering it here in our address window, 30117. And let me just adjust this window so we can see it. And now here you can see address 30117 does indeed contain the value of 13, which we would expect because that's what our program told it to do. Our program told it to define byte or save a byte of data with a value of 13 at the memory location, which is indicated by this print CR label. And print CR we know contains a value of 30117. So address 30117 contains the byte value of 13. So now let's go and take a look at this Health STR label that we defined, which should point to memory addresses, which should contain the string of characters that we have indicated here with the word health in it. So let's go and take a look for our Health STR label. And I'll go back to my Labels tab and look for Health STR, which is right here, Health STR. It contains a value of 30124. Let's again go back to our disassembly window and search for 30124, which is right here. So 30124, as we know from our program here, is used to store some bytes of this string that we entered. So it shouldn't be containing any assembly language instructions. It's just purely storing bytes that we're using as a string of characters. Although our disassembly window here has converted those bytes of data into assembly language instructions like jump return not zero, load C, load B, but we can just ignore those because we know that we're using these memory locations to store bytes representing a string of characters. But let's see if we've actually stored the correct characters that we're expecting. Now, how can we check that? So let's go ahead and take a look at the bytes of data that we've stored. And I'm going to do that by looking up the codes for the different characters used on the Sinclair spectrum. So I'm just going to open up the user manual for the Sinclair Spectrum computer, which is this here, which I expect should contain a listing of all the different characters and their associated codes. So I'll just take a look here. And here, if I look at the table of contents, it says here the character set should be on page 183. So let's go down to page 183. All right, so here's the character set. And before we take a look at that, let's just go back to our program for a moment in our assembler. And let's figure out where we would expect these characters to be contained in memory. So our health str label is indicated over here on our labels tab as having a value of 30124. So we would expect address 30124 to contain the first character in our string here. And this string contains, it looks like 2 spaces followed by the word health. So address 30124 should contain 2 spaces followed by the word health. So let's go and take a look at address 30124 in our disassembly window. 30124, you can see here, contains 2 values of 32. So 30124 contains the value of 32, and then the next address, 30125, also contains the value of 32. And from our string here, since our string starts off with 2 spaces, we would expect 32 to be the code for a space. So let's go back to our manual and confirm that. And we'll go down to code 32, which is right here. And yep, sure enough, 32 is the code for a space. So let's go back and take a look at the rest of our codes. And the rest of the memory addresses contain the code 72, then 69, then 65. So let's check those out. So 72, 69, and 65. 72 is right here, which is the letter H. And 69 is right here, which is the letter E. Then 65, which is right here, which is the letter A. So it looks like these memory addresses do actually contain the string that we assigned them, which represent the letters in the word health. So the letters H, E, and A represent the codes 72, 69, and 65. And back in our disassembler, that's exactly what we have, 72, 69, and 65. So we can see that is how we can use the define byte instruction to store a string of characters in memory locations. Now let's take a look at something else. I'll just close my debugger window here. And let's take a look at the final instruction I want to look at for today, which is the DEFW instruction, which stands for define word. So if we take a look up here at this DEFB or define byte instruction, this assembler directive is used to store a single byte of data. In this case, the byte has a value of 13. But what if we want to store a larger number that is larger than 1 byte? As we know, a single byte of data can only store a value ranging from 0 decimal to 255 decimal. And if you're not sure exactly why that is, you can go back and watch my video where I discussed about the different counting systems, including binary. But let's say we wanted to store a value in memory that was higher than decimal 255. So in this case, we can use the DEFW instruction, which is define word, and a word stands for 2 bytes. So 2 bytes of data, which represents 16 bits, can store a decimal value ranging from 0 to 65535. So we can use this define word instruction in this case to store a value in that range. So in this case, on this line, you can see you have a label called gold, and the label called gold will contain a memory address which contains this word of data that we're now storing in memory. And so a word of data, which equals 16 bits, which represents 2 bytes, will obviously need 2 memory locations because only 1 byte can be stored per memory location. So in this case, this address called gold here will contain a value that represents the first memory location that will contain 1 of 2 bytes of data that represent this value here of 500. So let's go and see what values we would expect that to break down into. And I'll do that by opening my calculator here. And here I am in programmer mode in my calculator. So let's enter a decimal value of 500. So here I'm in decimal mode, as you can see. There's a little blue thing here. And let's enter 500. And now we can see that the decimal value of 500 equals a hexadecimal value of 1F4, which also equals 01F4, with 01 being the high byte and F4 being the low byte. And since our machine code program always stores the low byte first, we would expect to find the value of F4 in memory followed by the value of 01. And that's going to start at the address indicated by this gold label. So by looking at our labels tab, we can see that our gold label starts at address 75CB hexadecimal. So if we go back to our disassembly window and we're now viewing in hexadecimal mode, we can see that address 75CB is right here, and it contains a value of F4 followed by a value of 01, which convert into the decimal value of 500, which we have assigned in our assembly language program right here. So that's how we can use the define word instruction, or the DEFW assembler directive, to store 2 bytes of data in our assembly language program. So we can see how valuable it is to use these assembler directives, even though they don't get converted into machine code instructions and get executed as part of our program. They are very valuable features of the assembler, which saves us a lot of work and makes it really a lot easier for us to be able to program and create assembly language programs which get converted into machine code to make up the games that we're going to be developing. Alright, so now let me just show you the part of this which may be confusing, which is if you take a look down here where I've got my EQU $ statement here. Sometimes this EQU statement could be used to define a particular value, which in this case down here you can see it's used to assign this value of 8252 to this labeled called print str. But in this case up here, we have EQU followed by a $ and no value following it. However, in both of these cases, neither of these lines of code actually take up space in memory, because remember, all this is an assembler directive to assign this particular value to a label. And also remember that these labels here, for example, this one, print str, this is being assigned a specific value of 8252. It's not being assigned an address. So if we take a look down here, we have another line here that starts out with a label called health, and it's being followed by this DEFB, or define byte word, that also is followed by a number of 100 in this case. So in this case, this label called health is actually being assigned a value that refers to a specific memory address, and that memory address is the address that contains this byte of data with a value of 100. Now, where the confusion can come into play is the way that I've actually structured this program is probably not ideal, because if you take a look at this, you would expect from this program this label called health would be assigned a value that contains the memory address that contains this byte of data with a value of 100, which it does. But if we look over here at our list of labels in our debugger, we don't see a label called health in here, do we? But we do see this label up here called strength strend, which is right here. We can see that this label called strength strend contains a memory address of 30154. And here's where the confusion comes into play, because now since this strength strend label is not being used to save any data, there's no data after it. And similarly with this print str label, again, since it's an EQU instruction, it has no data being saved as well. And same for this print num label, it's not saving any data in the program as well. So the next actual byte of data in our program comes all the way down here in this line that starts with this health label, and it's saving this 1 byte of data containing a value of 100. So in this case, the program is using this strength strend label to indicate a memory address, which indicates the next byte of data in our program, which is actually this 100 value down here. So probably what I should have done is reorganized my program so that I put all the EQU statements maybe at the end, so that we don't confuse the labels that are pointing to memory addresses with labels that are used to store specific values. So in this case, you can see we have our strength strend label contains a value that points to our next byte of data, which is down here after this DEFB instruction, which we would expect our health label to be pointing at that. But you can see in our list we have no health label, so that creates some confusion. And here if we take a look at our disassembly listing, you can see that it actually lists our labels in our disassembly program as well. So here if we take a look at address 30020, the instruction being stored there says LDA, comma, strength strend, when actually that instruction should say LDA and then health here in brackets, which we can see in our program here. would be right here at line 19, where it says LDA and then health in brackets. So although our program has been written using the health label, our disassembly is showing it as using this strength strend label, because that's the first label that's used in our program before the next byte of data, which should be down here after the health label. So like I said, it may be best to avoid this confusion by maybe putting the EQU statements at the end and then putting all the DEFB statements ahead of them so that we avoid this type of confusion. So I hope this all made sense and this was all useful information to you, because it's going to be very valuable in our game development journey. Now that we're using an assembler to create our assembly language programs, we might as well make the most of it by using these built-in assembler directives and these built-in features that's going to make our lives a lot easier. So hopefully that gives us all an appreciation of these incredible features that assemblers give us to allow our programming lives to be so much more easy than they could have been if we had to program in pure machine code. And hopefully you'll make use of these features in your programs as well, because they really make programming a lot of fun and really enjoyable if you're making Z80 assembly language programs. And hopefully you're well on your way to producing some games for the ZX Spectrum community or the ZX Spectrum Next community to enjoy. I feel like our journey is going well so far, so let's just keep moving forward. And as always, I thank everyone for watching, and I also want to thank everyone for actually liking my videos and commenting on my videos and watching my videos, because really it obviously takes a long time to produce these videos. I appreciate all my subscribers and everyone who watches my videos and comments on them and likes them, but really I'm not doing it to increase my viewership in the YouTube world. I'm really doing it to try and share my knowledge that I learn along my journey with any of you who might be interested in trying to learn to program or develop games for the Sinclair Spectrum computers or the ZX Spectrum Next computer. And I'm really glad that my information is able to help some of you as well. So thanks again for joining me on this journey, and we're going to just keep going and keep moving forward, and we'll see you next time.